Let us consider hollow copper tube and the solid steel bar as shown over here. The outer diameter of the copper tube is DO as we have indicated over here, and inside diameter is DI. So this inside diameter is same as the external diameter of this steel bar, and therefore we have written DI is equal to D. The metal thickness is T. So therefore we can say that the outer diameter will be nothing but, from figure we can say that it is nothing but inside diameter plus 2 times the thickness. So DO is equal to DI plus 2T. Now let area of hollow copper tube is given by pi by 4 DO square minus DI square. AST is the area of solid steel bar, and that will be given by pi by 4 D square. And suppose the axial load which is acting on this particular composite section is P. So composite section is nothing but the section which is consisting of 2 or more materials. So here we have taken into consideration the copper tube and steel bar as the 2 different materials, and inside this particular copper tube there is a steel bar which is fitted. The first important condition for the composite section is the deformation in copper tube must be equal to deformation in steel bar. Now we know that deformation is given by PL upon AE. So it is PL upon AE for copper tube is equal to PL upon AE for steel bar. If the length of both the section is same, then that L will get cancelled from both the sides, and we know that we are left with P upon AE for copper is equal to P upon AE for steel. Now we know that this P upon A is nothing but stress, so it is stress upon E for copper is equal to stress upon E for steel. Now just cross multiply by this particular term. So sigma Cu will get cross multiply by this EST, where E is the modulus of elasticity. This sigma ST will get cross multiplied by this ECU, where ECU is the modulus of elasticity for copper. From this, either we can find out the value of stress in steel is equal to stress in copper EST upon ECU, or you can formulate in terms of stress in copper in terms of stress in steel. So we know that stress is nothing but what? It is load upon area. So over here P upon A is nothing but sigma, and that value we have substituted over here. Now the second important condition is that the total axial load which is acting on the composite section will be, some part of that will be shared by the copper tube, plus some part of that particular load is shared by the steel bar. Again we know that load is equal to stress into area. So in place of P we have substituted sigma into A. So it is sigma of copper, that is stress in copper multiplied by area of copper, plus stress in steel multiplied by area of steel. The first term as it is. Now in place of this particular sigma ST, we have already formulated that sigma ST is given by sigma of copper, that is stress in copper multiplied by modulus of elasticity of steel divided by modulus of elasticity of copper. So this particular term we are substituting over here in place of this sigma ST. Now we can take this sigma Cu common, as it is common from both these particular terms. So if we are having area of copper plus EST upon ECU into area of steel, and hence we can easily calculate the value of stress that is developed in copper tube. That will be total axial load P divided by this term, which is nothing but area of copper plus EST upon ECU into AST. Once we know this particular value of stress in copper, we can easily substitute that value over here in this equation. So in this particular place of sigma copper, we can substitute the value that we have obtained, and we can obtain the stress in steel. So in this way we can find out the stresses in composite.